Alright, welcome back for lecture 20, ME422, Cool Weather in California. Previous lecture, we looked over brief idea why the California has cool weather compared to the east coast of Korea in terms of atmospheric conditions and ocean condition. And you also look at the sea surface height, sea surface temperature, cold water near the coast, and they have gradient away from the coast, and they're nice features of turbulent motions. And we watched the simple movie clip to describe the upwelling when wind blowing over parallel to the coast and wind-driven circulation deformed subsurface thermocline, and that generate cold water on the bottom, high nutrient water to the surface near the coast. And you see that the front near the coast, and that related to the phytoplankton blooms and zooplankton fish abundance. Uh, in the starting point, we use the cool weather in California because the cold water, but this is wind-driven circulation, one of major features in environmental fluid and oceanography, and that the common area. We also looked at the chlorophyll concentration maps in the globe. There are 5 regions of eastern boundary. So we stopped some point. I'm going to continue on what happened. So as you can see here, cool weather in California, cold water near the coast. There are the filaments and eddies. Similar to that, the central northern California to Oregon State. Not only the cold or cool water and atmospheric condition from the polar region, it dry and cold, and also generate nice features, and it requires steady wind, which is our case for upwelling. Compared to the east coast of Korea, the wind coming from the southeast in this case in the summertime. Let's look at the July 24 8th. That means in the middle of summer, which is the wind blowing from the south. So it contains all the humidity and muggy wind generate this event, cold water event. What happened? Why is it cold water coming up? And example for eastern boundary, California. If you look at here, California, Peru, Bengal Canary, Western East Australian current area. The maps are a little bit shifted by that, but compared to the SST versus chlorophyll concentration, they are coherent structure. Cold water, particularly upwelling, generate chlorophyll concentration abundance related to phytoplankton bloom. So we can think about why that happens, like upwelling in the coast. When wind blowing parallel to the coast, water moves to the right of the wind, and due to the mass conservation, bottom water surfaced. So in the opposite case, if you're blowing the wind parallel to the coast, but in the opposite direction, water transport to the right, and due to the mass conservation, water sink down following the bathymetry. This is two events we call the upwelling and downwelling when it happened to the steady state wind response near the coast. And this is an example for northern hemisphere. So you might imagine this cool weather in California and SST image by the upwelling event, wind blowing north to south, and cold water approach to the near the shore, and they marching or transit to the offshore. And the nice turbulent features and eddies, filaments. That's a turbulent motion we're gonna mention this class or other numerical simulation chapter. Right, so I'm gonna continue on why we have wind blowing uh, water transport, not the direction of the wind. Why is it 90-degree right in the northern hemisphere case? You might just imagine we are working on large scale fluid dynamics, and this fluid act on rotating frame, which is the Coriolis frequency. So somebody might already recognize wind and wind stress act on a fluid in rotating frame. In 1907, there's uh, a pioneer to examine this relationship, wind to the currents. We call the Ekman spiral. For example, if you have wind blowing one direction and surface, this wind momentum will be delivered to the water. This is the water depths from surface to the bottom, wind blowing on the top. This axis indicates the vertical axis. And if you imagine this water body is layered surface, below that, right? And this arrow indicates the direction of currents, surface currents, subsurface, below that. And this is schematic figures when wind blowing one direction, surface currents heading 45 degrees the right of the wind direction. As you get deeper, they will rotate, make a spiral. And if you integrate over the depths, specific depths, we call the Ekman depths, entire water move to the right of wind direction, we call the Ekman transport. Today we're gonna go over why, how we drive with this Ekman transport, Ekman spiral, based on the momentum equation. And that will give you what's the physics behind this phenomena based on momentum equations, and you can learn how you're gonna manage that features. As I mentioned, this is happening on the steady state wind and Coriolis framework. So you might imagine this is the wind stress which is blowing long time, and Coriolis frequency should be valid. That means your fluid motion has a scale, time and spatial scale enough to respond it. For example, uh, this flow time scale should be longer than Coriolis. If it's shorter than that, the term in the momentum equation may not be, we may have to ignore the Coriolis, but uh, to think about it over several weeks and steady wind happening in the California area, it typically it happening in springtime in California. Steady wind generate upwelling, so uh, the wind stress is pretty steady state, and water responds to that. And this is an open ocean case, so we're gonna move the domain to the shore to see more general description on it. However, I just want to give you wind blowing one direction. This Ekman transport is 90 degrees to the right for the northern hemisphere. This is the wind blowing, and white arrow, which is the Ekman transport, the same as the bottom figure, wind blowing one direction Ekman transport. So we're gonna look at what happened Ekman transport and Ekman spiral with the equation, and more detail will come with circulation in the coastal area. So we're gonna look at the Ekman balance with momentum equations. This is the simple copy that we have previous lectures. Acceleration first, uh, stress. I'm sorry, the vacuum term UVW, and differentiate with respect to the. Oh, I'm sorry. This should be Y. It should be X Y Z X Y Z, right? There's a typo. Sorry. Uh, and also Coriolis frequency terms and pressure gradients, then stress, second order stress divergence, and viscosity, gravity only on z direction. All right, so there are a couple assumptions that we have to consider. Uh, the first term will be steady state, which means long term motion. We are looking at long in time, steady state approximately, right? And also horizontal scale is longer than vertical scale. So if you're looking at uh, second derivative on the right hand side, it's much larger than, so this term will be much smaller than the other term because x and y horizontal spatial scale is longer than vertical scale. And no pressure gradient for now. And if you say linear term only, non-linear term ignore. I'm sorry, there's a typo on the differentiation. And we keep the Coriolis force, which we call the Coriolis valid situation, to consider Coriolis rotating frame. F is the local Coriolis frequency. And remaining term, you might think of viscosity with du dz. This is a z-directional velocity second derivative. So we can substitute as the wind forcing with that. Do you remember the wind stress tau can be defined as d mu du dz, and du dz can be replaced with that, and if you plug in, you can have d tau dz, right, multiplied by over mu, right? So you can simplify these two equations with given assumption, and we only consider xy direction, not the z for now. Okay, and also z directional velocity term will be pretty small, so this term can be out, and mostly hydrostatic will be applicable for this case, but we are looking at horizontal motions when we have wind stress. So you can think of, if you simplify the momentum equation, the second order PDE coupled xy direction that case, in order to solve this one, you need boundary conditions. So we have z directional only. So if you rewrite in the next slide, I copied from the Kundu textbook chapter 13. They have nice presentations and explanations. So please refer that chapter to see more details on the Ekman theory. So you can copy from previous equation to simplify the form here. Coriolis extraction, viscosity with du dz. There was a partial term in the previous one, but we only consider velocity u as a function of z, and v is a function of z only, so they put it in the regular ODE differentiation term. And y direction fv viscosity with d second order dz. And as I mentioned, this is a differential equations, and if you solve this one with boundary condition, you will see u as a function of z, v is a function of z, but they couple, so we're gonna put together basic idea will be u plus iv. But before that, we have to think about the boundary conditions. And as I said, this is the we assumption here, and we consider, and we'd like to know what happened when wind blowing steady state. So wind blowing, that means the wind stress will be applied at the surface. If you define z equals 0 at water surface and going positive downward, so you have z equals 0 going downward, so it's infinite depths. Surface, we have wind stress, which means rho mu d du dz will be stress at the surface. And if you imagine on the bottom of water column, infinite depths will be velocity will be 0. And also, if you just consider only one directional wind, which means we have only tau x only, x directional wind blowing, y directional wind is 0, right? We don't put it in the direction here, but if you put in the surface boundary condition only has x directional wind, you can put it in this way. But if you wanna y directional wind only, this will be 0, and rho u mu dvdz will be tau, right? Vice versa. So in the textbook Kundu, they use only tau x applied. So x direction, if you have xy coordinate, we are looking at wind only blowing on x direction, positive. And infinite depths, which means if you go deep or away from the surface, the velocity will be 0 because there's area no influence by the wind stress, even though it's steady state. So you can use one for surface boundary condition, the other one is bottom boundary condition for given differential equation. So suggesting that if you multiply by I, imaginary number, and add 2, and if you substitute by capital V as a u plus iv, you can simplify the equation, coupled one, in this way. If you multiply I, if will be coming out, then you can easily combine the capital V here. And this is second order ordinary equation, so you can assume V is A times something Z, which is a g-directional variable only. V minus E something Z, and apply the A and B is constant here, and you can compute some sort of characteristic, right? We use A sigma Z, A E sigma A E sigma Z plus B minus E sigma Z. We don't know yet, but if you solve that, you can come up with this one. And one of homework assignments related to how you're gonna solve that. So please fill in the details, right, in a logical way. And delta is defined by viscosity twice of viscosity divided by F, and square root of that they call the Ekman layer. So d is delta is the length dimension, uh, meter square per second divided by 1 of second, square root of that is meter. So you have z is a z directional dimension. 1 plus I will be constant. So you can think of z and delta is going to be same dimension. In case if you consider Euler expression like E plus something, you can use the cosine and sine. In that case, you might think of this is the should be radian units. So sometimes I used to use a 2 pi over here, or vice versa. If you put a 2 pi here, z may contain 2 pi, and all the ratio of z over delta will be some number, fraction, like 0, half, a quarter, 3/4, and so on. But if you make a consistent notation, it will be fine. So if you say delta is given this value, think about how we're going to define, right? So in case z equal to pi delta, half pi delta, and so on, you can get the value, right? So if you apply the surface boundary condition and bottom boundary condition, you can come up with what's the A and B. And A is given as this way: in stress times Ekman depth with 1 minus I, and you can put it back in here and compute the B. I think B should be 0, right, when it has infinite. If it's infinite, I'm sorry, when it has infinite, it should not go to infinite, right? Right, because the field must be remain and z equal minus infinite. I think this, if you say, I think this is kind of typo, I guess. Z should be positive upward, and we have this is minus infinite, right? That means this term will be disappear. Otherwise, it doesn't make sense. Okay? Sorry about that. So if you put it back in A and B in the B, capital V, you can rewrite the equation U and V as a exponential function z over delta, which is the fractional relationship with depths and Ekman depths. So this is u over z, right? There is no time, only z directional distribution. And there is cosine and sine term will be assigned to u and v. Cosine will be z over delta or quarter pi, and similar to the v is sine. So you might think of wind stress applied to the right, as we remember wind stress will be only applied to the u direction, x direction. Y direction stress will be 0. So they draw the hodograph, which is the velocity transition, right? Compared to trajectory, we learned that, right? Hodograph is they connected, or they examining the velocity transition over time or in space. So u and v is axis that we are looking at in the center. And when it has 0, which means z equals 0 means z over delta is 0, that means the surface, right? That means this one will be 1 and 1 cosine pi over 4, and sine pi over 4, they have the same value but it's negative, so it's going to the 1 to 4th quadrant, right? Wind stress applied to this direction, and angle is 45 because you see that pi over 4 and heading that direction. Okay, and let's look at the z over delta as the pi over 4. Okay, oh, they put it in the minus z over delta, right? Not the z over delta, sorry. So it makes keep confusing, right? So please stick to the consistent convention to set the z coordinate positive upward. And if you prefer, when you put it in this a over here and make a sign convention is consistent, so that you can determine you're going to look at the z over delta or minus z over delta, right? I used my copy, but with handwriting, but I just excerpt from the textbook, but I thought it's the same, but it's a little confusing way it is written. So if you choose pi over 4, okay, when it's minus z over delta, this will be pi over 2, pi over 2. That means 0 cosine pi over 2 is 0. This will be 1. And you might see z over delta will be decrease with depths because this is negative sign embedded here, right? So heading direction will be 0 and 1, which is the v component only exists, and it should be negative, right? This is positive 1 and negative value, and direction will be goes that, and amplitude will be reduced compared to the surface because exponentially decay, right? And as you move on, there will be rotate as you increase the angle, and their amplitude will be reduced. So if you look from top of Ekman layer, which we have this one, if you look from top, wind blowing and subsurface, their spiral, their wind-driven currents will be reduced, and there will be rotation. And when it comes to the northern hemisphere, it's clockwise. Otherwise, it's counterclockwise. But if you say all depend on the definition of delta here, because F involved, and you might think of F is negative, that means square root inside of there's a minus sign, right? That comes out the I, and that affects the whole equation. So if you have northern hemisphere case, southern hemisphere case, You have to think about it. And the figure on the right hand side here, they plot as of u and v as a function of depths. U over here, v is a thick curve, and they divide into the depths as a function of quarter of depths. So as you get deeper, their amplitude, which is the distance from the zero axis, will be reduced, and they rotate, so they looks like uh, not they doesn't look like the decreasing in a simple pattern. They as they make a spiral, they kind of twist it each other and all the way, right? So you have equations, right? And before you go further, I just want to show you, based on the momentum equation, you can simplify, and with the boundary condition, you can see what will be the u and v currents in a given condition, and you end up being looks like that. Is profile, the vertical patterns, and if you look from top, there will be make a spiral. So one motivation of this work, there's a phenomena, and with the basic momentum equation, we can learn how and why this happening starts, and you can understand the basic physics. So u is a function of z, v is a function of z. But take a look at it closely. I took a little different way that I did, but if you apply the stress tau y, v directional wind, you can see that little different form and should be consistent with this spiral, right? That case, if you have only tau, go to the north, spiral starts over here, and similar pattern. So everything should be 90-degree rotate on counterclockwise. That case will be response of wind stress on the ocean. So if you have U and V profile, you can integrate over Ekman layer. So if you consider volume transport, which is the velocity over depth integration, you can come up with what's the water movement over Ekman depth with delta. Okay, so you integrate it. I'm sorry, uh, so if you integrate over depths, entire infinite depths, um, you can get the Ekman transport. So U directional is 0, V directional has negative value here. So if you have tau apply, the transport is goes the direction minus V direction only. So going that direction, entire water is moved to the 90-degree right of the wind direction. And you might think about whether this is Ekman layer only or infinite depths. Please look at the refer the infinite depths for now, uh, because as you go from the surface to the specific depths, they will be reduced by the Ekman layer. I'm sorry, the influence of wind will be reduced from surface to the specific depths, and may not be affect that much if you go further. So they use infinite depths. And also, I have to say, Ekman depths is given in this way, but Ekman depths technical definition will be when it has 180 degree, like the depths of the currents driven by wind compared to the 180 degree from the surface water. So we had 180 degree when it has the opposite direction of surface current. That's gonna be Ekman depth, but they just use the Ekman layer, the simplest case that to make a simplify the differential equation, but technical definition will be when it has 180 degree direction of the surface current by the wind. So Ekman depth will be over here from surface to the bottom when that current is opposite direction of surface current. Okay, I didn't go that much smooth way, but please review with the equations and textbook. Then you can see, you can fill in the gap in detailed derivation. Maybe you can learn from the homework assignment too. And you can also consider this boundary condition as a finite depth. That means surface condition will be the same. But if you have depth equal h, in case minus h will be bottom of your boundary condition. So you have finite depths, z coordinate positive upward, and specific depth minus h is equal to 0. So in that case, your uh, solution will be just very different hyperbolic condition. So that affects the spiral a little bit, right? So in case if your infinite depth is deep water or open ocean, but if you have finite depths, if you're near the coast, you might consider it as a finite depths. And I'd like to show you the MATLAB script that I have. As I make this one as a movie, right? You can copy of this script, right? And you can write your code by your own and run your script. Rather than I distribute this one, it's better to type by yourself, right? Or you drive it. I I think that's the learning process. So please excuse I did not distribute this one for educational purpose. Huh? So this is MATLAB. You can define the constant for kinematic viscosity, density of water, mu, dynamic viscosity is given by that, right? And if I apply tau y in a given this number, depth is h 10 meter. Let's say if I live in 37.5, which is Korea, Northern Hemisphere, f is given 1 per second units, and s is gonna be similar to that one, right? F over mu, and I, you see that why I took this one. So if we use this part, right, in front of V, which is S, can be characteristics of the differential equation. You see that if you solve this one, Ekman depth is the square root of 2 nu over F, and Z is the negative axis, so positive upward, and you can put as a multiplication of Ekman depths. I put it in the pi here to make it better dividing of the depths, right? Pi times something, Ekman depths, right? 0 to 1, I divide the 50, same constant being, right? And I'd like to apply two axes, which is the infinite depths. Infinite depths is the second one. First one is infinite depths. If you solve momentum equation and express as a function of exponential function, this is the individual component, but I put it in the convention of I. So if you solve this one, you can come up with that. I could be wrong, but let me know if I'm wrong. And this is the infinite depths, and W2 will be finite depth, the hyperbolic function, as you have depth H, capital H will be applied. So if I run this one, you can see uh, the profile. For example, you have 10-meter depths given stress tau y, and as I plot in U and V at the same units, minus 5 to 15, minus 5 to 15, this is a square box. So diagonal will be 45. So wind blowing in y direction, and surface current will be 45 to the right of the wind direction. As you get deeper, as you make a depth layer Z, 50 layer, and all the way they make a spiral. And one thing difference will be uh, blue is a finite depth H is 10 meter, and infinite depths. So this is a shallow water blue, deep water is red, and they make a spiral as you've seen in this, has 90-degree difference, right? So I only plot in the Ekman depths up to surface to the 180 degree, right? They draw everything on a spiral, right? So keep in mind they have slight difference between finite and infinite depths. You might think of an Ekman depth was estimate 3 point something. So water depth is 10 meter, for example, and Ekman depth is shallower than that, right? If I put it in the 100-meter depths, it's almost similar because Ekman layer may not affected by the bottom, so infinite to the finite, they have almost similar patterns, but if you get close to the shore, uh, it will be affected by that. So if you look at the spiral, right, from top view, side view, and the reason that we only plot it on the up to the Ekman depths, which is a 180 degree opposite of the surface current, right? If you want to see more, you can see more, right? You can put in the z direction. Z axis is 2 times of that. If I put it in the 2, it will be 360 degree spiral, right? So you can see that 180 and 360 degree spiral. You see that, okay? This one too. So arrow, this is in the where you apply the wind, and surface is that deeper, make a spiral, and 180 to 180, 36 degree spiral here. So one thing I'd like to highlight here, we have equation. You can visualize with a simple MATLAB script. So you learn when you change the value and when you change the situation, why that looks like, how that looks like. Okay, so I think it's one of the beauty of environmental fluid or fluid mechanics. You have theory, mathematical expression, so that a lot of people call it applied math. So you can visualize the fluid motion. In this case, we only look at the velocity profile with depths, but it's pretty instructive. Okay. And I'd like to switch the gear to whether what happened on the surface currents, surface circulation by the wind, open ocean versus coastal area. I draw by my hand. Please excuse this. It's a little uh, funny or not scaled by completely real case, but I describe by my word, right? Open ocean case, if you blowing the wind, surface only is 45 to the right when it has northern hemisphere case. So surface current goes 45. And coastal area, if you look from right hand side, this is water level. This bottom topography, you're looking at the three-dimensional view. This is shoreline. If you go to beach, you're standing here. This is water and water depths. And I'd like to ask you what happens if you blow the wind in a different direction. For example, open ocean, wind blowing east, north, or west. What happened? I prepare this way. Wind direction east, north, west. What will be the surface current if in northern hemisphere? 45, 45, 45 to the right of wind direction. And also Ekman transport will be integrated by that. Infinite depths, you can see to the right of the wind direction, 90 degree. We call the isotropy. That means wind-driven surface current only depend on wind direction, but that doesn't mean wind blowing which direction, east towards the east, northward, westward, doesn't matter their response. Like not a function of direction. That means isotropy is constant direction. But let's think about coastal area when it has wind blowing east, which is the onshore. So you're standing here, wind blowing towards you, steady wind. What happened in the water? And what happened in the wind blowing to the north, which is parallel to the shoreline. And what about wind blowing on offshore, not the onshore? In the Ekman theory, Ekman transport, uh, we learned in the previous lecture, and we're gonna look at more. But I'd like to say I'm just looking at the surface circulation only. So I just want to highlight what's the direction of surface currents. For example, if you have there's uh, oil spill, crude oil accident happening in the open ocean or coastal area, and you have to remove that oil. And at the time, wind blowing one direction all the way, and you can think of, oh, we have to go 45 degrees of wind direction, so you can deploy your fence, right? And also you can think of surface circulation in the coast where it goes, oil spill goes, right? You might have to figure out the direction. So in terms of that direction, I'm just describing this slide here. So when it has, if you look from top of the coastal area, you can think of this is the coastline and wind blowing on east onshore, parallel to the shore, offshore, and parallel to the shore. What would you like to think surface current looks like? For example, blue indicates completely 45 degree as we see in open ocean, or green will be less than 45, right? Red is greater than 45. Okay, one thing difference between open ocean and coastal area, you have wind surface currents generated by that, and coastal area has constraint flow or water may not penetrate in this boundary. So you have to think about wind blowing one direction. Wind is okay, wind is maybe passing through the air, right? The boundary. But what I'm saying is the fluid of the water may not passing through. So if you move your domain to the open ocean to the coast, their directional response may affected by this constraint. If you have onshore, it may be 45, but the 45 hit the coast should be detour, right? So their response may not be the exactly 45, it should be greater than that. Does it make sense? Does it make sense? And about the parallel to the coast, maybe 45 initially, but this flow may hit the coast, may not go right beyond the boundary. So their influence, boundary influence, may affect that, and green less than 45 happening. How about the wind direction when it has offshore wind? If you have offshore wind, surface current is three different cases as we see in here, and there's no constraint to force the flow, water movement. So I think the 45 will be here, and this case will be 45 the same. But what I'm saying here is you have wind blowing, and wind driven current has constraint that will be affected by that, and wind driven circulation will be changed. But how can you explain with the equation? Right. Okay. This is Ekman theory. You can apply it wherever you which direction of wind there will be 45-degree surface. Why you keep saying not 45? Okay, here is the reason. Before that, I'd like to say we call the anisotropy, which is the surface current circulation depend on the surface wind direction. So whether onshore, parallel to the shore, it generates different response. So your current response, wind-driven surface current, as a function of direction of wind. That means anisotropy. There is a directional preference. Opposite way, the open ocean, there's no directional preference. If you apply the wind one direction, response will be, you can imagine, 45. But coastal area, there's a constraint by that, right? So it may not be always 45. Okay, so I'm going to continue on the discussion why or how we can justify this less than 45, I'm sorry, more than 45, and this less than 45. can imagine wind blowing that direction, right? There's Ekman transport because of frictional balance. When Ekman transport, when you blow the air over the water, it also Ekman transport, but there's no constraint, so flow will be continue on. Or if there's a boundary, water can be piled up at the coast. Let me repeat. If you have wind blowing, there's frictional balance, there's movement of water, and also if you integrate over depths, you have Ekman transport that will move the water onshore and offshore, right? And this boundary affects that, right? Like if there's boundary, there's no sea level change, but in given boundary, the water will be piled up or will be piled up the other way, right? It generates relative difference of sea level that generate pressure gradient. So in this final form, we may have to keep that in order to understand the coastal circulation. Open ocean case will be fine, but Ekman transport generate pressure gradient that affects the surface current response. Trust me, right? So we are not going to looking at this pressure gradient, but in coastal area you're not looking at it as an equation, but in the coastal area I will describe the dynamics only not using the equations. All right, so isotropy versus anisotropy doesn't matter for the direction. It matters with direction. So if I re-summarize Ekman spiral surface wind applied to the water and that generate transport over the depths of Ekman influence, wind influence, surface is 45 degree from wind direction in the northern hemisphere case. So one thing you may apply for that is upwelling and downwelling happening in the coastal area. So if you have wind blowing, steady wind, 90-degree transport will be happening. If you look at the layer, we call the Ekman transport, effectively working on here, and mass conservation, cold water, high nutrient water will be surfaced. Other case is wind blowing the other direction, Ekman transport, pushing down the water. Okay, I'm gonna looking at what happening coastal upwelling and downwelling in terms of sea surface height and picocline or thermocline. All right. Uh, so left hand side will be similar figure, sea level, and the bottom and shoreline, and wind blowing in this direction, and wind is opposite direction. So you might imagine this is an upwelling case. Wind is heading this direction, Ekman transport to the right, and if you draw the surface layer by the wind, water is moving out, and due to the mass conservation, the green part will be surface. We call the Ekman. Uh, Transport generate upwelling, coastal upwelling, so water will be relatively cold from the bottom and surface. And there's a front generate here. And if you look at the right hand side, it's the repeating same one in the bottom bathymetry water line, let's let it flat, and shoreline here, window blowing, transport, generate, and water will be sink down. Relatively warm water coming down. We call that downwelling. And I'd like to look at what's the sea surface height and thermocline case. Uh, if you have upwelling, let's say you have flat iso density or iso temperature line, and when it has upwelling, their flat one is gonna be raised up, right? It raised up this way. So general patterns of iso density line will be flat. When you apply the wind by the command transport, it's gonna be going upward. And also you might think of water is moving that direction. I agree there's a balance by the mass, but it's relatively cold water here. And if you imagine the sea surface height, the offshore will be relatively high. So green is the sea surface height elevation patterns. And if you look the other case, wind goes to the south north, water will be transported in this direction as you see in the top, and iso density line will be downward direction, not the upward direction, downward tilting, okay, by the downwelling, right? And if you say the sea surface height will be goes to water will be piled up, even though it's mass conservation, but relatively warm, water will be piled up. So sea level is relatively higher in the shore compared to the offshore. Its typical distance will be 50 to 100 kilometer range. Might say, yeah, about 50 kilometer or so, 50 to 100 kilometer range. So this is a circulation patterns, but if you see density, iso density line, and there's a building case at the front here, and if you see the sea surface height will be it goes to the higher and offshore, lower than onshore, opposite for downwelling. If you look from bottom figure, I'm sorry, uh, figure, another, yeah, okay, I just highlighted sea surface height versus iso density or temperature contour. They are going to, they have opposite phase. Can you imagine? Like this is the shore here, it goes up and down, and this goes down, it goes up. Do you remember that we had example in the density uh, horizon density gradient part when we have like flat, like iso pressure line and iso density line are parallel, and when I put on the same density of water on the top of the tank, their surface layer and their iso dense layer will be has opposite phase. So this is an example. Nature made that ideal case or experimental case. Nature given nice features, surface height tilt, and iso density line is the opposite phase of surface. Okay, so consider if you have surface height tilt, you might think of pressure gradient goes that direction. Coriolis balance is that there will be just reciprocal currents going to the north to south, the same way as the pressure gradient going that direction by the tilting of surface height, and Coriolis balance that, and current will be to the domain, right? So you can think of wind blowing in one direction, north to south, and geostrophic currents generated by the surface height is the same direction of wind direction. in the downwelling case, it's just a bit height is higher in the shore. Wind that goes that direction, right? Higher. That generates a geostrophic current on that direction. So wind generate transport, Ekman transport, and also geostrophic current as well. So uh, in terms of magnitude wise, it's relatively small compared to Ekman currents, but things happen in the near the coast. All right, so we're gonna watch a more comprehensive movie next time, and I'm gonna stop and see you next time. Thank you.